In this video we're going to look at some basic elements of the program Phreeqc, and we're going to look at it with regard to a tap water. So let's have a look at this one. This is a sample. This is the opening page of Phreeqc. I've got data down here which explains some tap water compositions for a typical tap water in Yorkshire, and it's a low alkalinity tap water. This is what Phreeqc reads, this half of the page. So temperature is 25 degrees C, the pH is 7.35, PE is usually set at 4, redox it says is PE, units, the default units for everything is parts per million, which is the same as milligrams per litre, density of water is 1, then it's got down the values. So alkalinity, it's we've got it down as milliequivalents per kilogram. And that's milliequivalents means the amount of hydrogen ions you need in order to reduce the pH down to 4.3. I'll talk about that in a bit. So remember, it's at pH 7.35. We're going to see its buffering capacity, how many hydrogen ions it takes to go down to pH 4.3. Then it's got the concentration, so calcium 20.3 ppm or 20.3 milligrams per litre. There's the chloride, potassium, magnesium. This one here is a nitrate actually, and the nitrate, when you write down the nitrate, that figure 0.84 refers to 0.84 parts per million or milligrams per litre of nitrogen. So it's not 0.84 milligrams per litre of nitrate, it's 0.84 milligrams per litre of nitrogen. The sodium is 11.1 ppm or milligrams per litre. Then the phosphorus, it's actually P stands for phosphate, but it's the 1.2 means it's 1.2 milligrams per litre of phosphorus. So it's not 1.2 milligrams per litre of phosphate. It's 1.2 milligrams per litre of phosphorus. But in the solution, the program looks at the P and says that's phosphate. So it's perhaps a little bit confusing there, but normally when you write down in tap waters, you'll say something like it's 1.2 milligrams per litre phosphate, and then you write as P, capital P. The S is a little bit different. So the S is actually defined as 40.7 milligrams per litre of sulfate. So not of sulfur, but of sulfate. I know I've got up here it's ppm, but ppm means the same thing as milligrams per litre, so you bounce backwards and forwards. So this is the opening window. Everything is also repeated down here on this left-hand side because this is Phreeqc Interactive. And if I want to input data into this, because the data is already there, but if I double-click the flask just here, double-click it, you'll open up a box here, and everything I've got here is actually inputted here. So when you actually set out your screen, this screen, it's easier to go to this box here and write it in these tables. So we've got all the information here, individual element input. You can put the default units there. I could have put down, I've got ppm, but I could have put milligrams per. It says per kilogram, so there's nothing's per litre, it's always per kilogram in Phreeqc. I've got, leaving this black thing here, it says charge balance, it says none. So at the moment I'm going to leave that as no charge balance, and I'll talk about that later. If I look at this box, all my values are down here, and the units are milliequivalents per kilogram for the alkalinity, but everything else is default unit. Default unit is ppm or milligrams per litre. There's all my data there. And to actually input something, let's say I wanted to put in some copper 2+, then what I do is I click the box for copper 2+, and then I would go to the copper 2+, and I would double click in there and put in my value. So let's say 7, and then here I'd leave it as default if I wanted it as 7 ppm, but let's say I wanted it as ppb, then I would find ppb and then I'd click that, and now it says copper 2+ 7 ppb. So I don't want copper 2+ at the moment, so I'm going to unclick that box and it's gone. So there's lots of different species you can put in to your program. Where's our sulfate? Sulfate is written here. Phosphorus, you'll notice it just says P. And the nitrate, we click the nitrate box, but actually the nitrate is read by the program as nitrogen. Well, it's in terms of its concentration, it's a nitrogen concentration that it defines, but actually it's an NO3 minus species in the program. So that's all the data. I'm going to say the last one, I haven't got any isotopes that I'm looking at, so I'll go back to general and I'll say OK. So that's all my data. And let's say this is my tap water. So I'm going to run it, and I'm going to see what Phreeqc does. So in running this software, you need a database. So the database I've got is a modified one. So if I just find the database, here we go. I've called it modified Mintech plus October 2014 file 6. I've modified it a few times. Basically, it's what's called a Mintech file. So when you get Phreeqc, Mintech is one of the databases. But I've added a few things to the Mintech file. So the things I've added basically are constants to do with lead. So, but I suppose before we talk about that, let's have a little look at some of the lists down here. Let's go down. It has to define all the elements that are present at the top of the software, and in doing so, it also defines their relative atomic masses down here. And I can't remember what the other column is. I'll keep going down. And then it's got some equilibria that it's got to define at the top. Actually, it's not equilibria, they're statements. And then down here we then do get equilibria. So this is equal sign is equilibria sign, and you've got some thermodynamic data as well, some enthalpy data. I go down. The ones like there's lots of data, because the database contains a huge amount of different constants. Some of the constants will be very good and accurate, and some will be less accurate. People won't know them so well. If I keep going down to the lead ones, these are copper. Only partly way down. There we go. There's all the lead. These are so constants for ion pair formation. So this is a lead 2+ ion combining with 3 Cl- ions to form a new dissolved ion species called PbCl3-. And there's lots of other lead, what's called ion pairs. So actually you tend to think of lead as just being Pb2+ in solution, but it's not. It binds with other ions, and it still stays as maybe as an ion, but it's called an ion pair. So these are all different ion pair equilibria. I keep going down, and at some point I get down to near the bottom, and these are start to be minerals. So things like vivianite and witherite, these are minerals, and these are their KSB, or the solubility product values. So you've got log K minus 8.585, and there's the equilibrium. It's barium carbonate. This is a solid, and then these are the ions that come together to form a solid. If I go down a bit further, all these are solids at the bottom. And here we are, we get down to the lead ones, and in my database I've got values that I've added. So for example, these pyromorphite figures, there are different values given depending on the publication. And so what I've done here is I've given the name pyromorphite and then said who it was that they did the value, and then they've given their value. There's another one, Maneki, has quoted one for minus 79.6, Gimmer minus 80.4. So all these different values are in there. Really what I should have done is perhaps referenced it a bit better. So I should have said where the paper came from. Anyway, coming down here, all these other minerals like plumbogamite are all there. So that's enough for the database. So that's it. When Phreeqc runs, it looks at this composition file, for example, what's in the tap water, and then it runs the Phreeqc using the constants that are in this database. So I'm going to go back to the Phreeqc interface. There we go. I'm going to run it. Now, when you want to run this, when it says run, it just means run the simulation. This is your data. This is your input data. What's going to be your output data? You can only run it if you can't run it from here. If you can see my little clicker, the blue bar, but you can run it once you get back up to where it says Phreeqc or Phreeqc C1. Then the little run sign appears, and then you press run, and you say start, and it usually says something like this one. It says, do you want to replace it? This is your file, the output file. So I've got an output file. It's called Phreeqc1, and I haven't changed the name. So I'm going to say yes, overwrite the previous one. And the same thing again. This is an output file, so the same name, but it says PQI at the end, and I'll overwrite the previous output file that I did. You don't have to do this. You can make a new input and new output file name each time. So I say yes. Simulation's done, and at the end you've got this screen, and the fast finding thing is don't press cancel, you just press dismiss, and then you've got all the data it's generated is down here. So it starts off, so you notice at the bottom of this screen, this is the blue one is the input that you did, the green one is the output. The database this is the database that you're using. So this is the database I showed you before. So go back to output. If you've got any errors on there, then they'll usually show up in here. And P, I can't remember what this stands for. Okay, we'll go back to the output, and the initial part of the output shows actually the input. So this is everything that you inputted in, and then what it does is it lists everything in terms of molarity. So all these values that you gave, for example, calcium 20.3, that was in milligrams, or sorry, ppm, but it's converted them to molarity, and so that, and the alkalinity, it says 0.465 milliequivalents, so that is in a molarity anyway. So it's just it's just say, but it's milli, so it's millimolar. Really, milliequivalents means millimolar. So therefore, it's given it's 4.65 times 10 to the minus 4. So this E is really another way of saying times 10 to, so it's to the minus something. And then let's describe the solution, because you said the pH was 7.35, you gave the pH is 4, activity water is 1, and it gives some data. And when it ran the simulation, what it found is the electrical balance. You try as much as possible when you're doing these simulations to get to an electrical balance of 0 when you're doing a simulation like this one, and a negative 6.875 to the minus 5 is pretty close to 0. It's pretty good. And also, if you have a look down here, the percentage error, this is percentage error is really a cation anion balance. So the thing needs to be as close to electrical neutral as possible. So you need to, when it does the simulation, it needs to have as many negative charges balancing as many as positive. And this is saying there's a slight imbalance, saying there's slightly more negative ions, and the error is minus 1.96. So you could get an error lower if you wanted to adjust it, or on the input file there was something which said charge balance, and you could charge balance it, and if you charge balance it, this thing would come out as 0. But I've not used a charge balance on this one, because you can manually do it as well. You can keep adjusting things until you get as low a percentage error as possible. Let's look at the species. So what it's done is, in the simulation, it's come to a final answer. So this is its final answer. This is what Phreeqc is saying is in your solution. So it's saying this is the concentration of OH minus ions, H plus ions, and H2O species. These are the concentrations. Starts off by telling what the total amount of carbon is in this solution, which is 5.201 times 10 to minus 4 molar. Everything's in molar now. But of that total carbon, it's made up of the following species: hydrogen carbonate, minus, dihydrogen carbonate, so forth down here. They're the calciums, they're the chlorides. You can see chloride is just present as chloride. Potassium is mostly present as K plus ions, but it's also a little bit present as KSO4 minus ions. Go down the list. Magnesium is a bit more this is called speciation, so it's a bit more speciated, a bit more different types of ions present for magnesium. Nitrate's just NO3 minus. Go down to the bottom, phosphate. Now phosphate is interesting because it's got species which are protonated species like HPO4 2 minus, but it's also got ion pairs which are protonated, which are combined with metal ions as well. So you've got an ion which is called calcium dihydrogen phosphate, and it's got a plus charge on it. And then you've got sulfate down here. So this is telling you all the dissolved species in this screen here and what they are. Right at the end, what it does is the database has got all the different minerals in, and what Phreeqc has done is any mineral where the ions listed above here are part of that mineral will find its way into here. So for example, calcium sulfate anhydrite has got calcium and sulfate in, and calcium and sulfate is up here, so therefore it's looked at calcium sulfate. Anytime you get down here, the first column is called the saturation index, and a negative value means that it's undersaturated. In other words, anhydrite is negative, and so it will be expected to dissolve in this solution. Anything that's positive will be expected to form. So if the first one go down the list is hydroxyapatite, that's got a formula Ca5PO4 3OH, so it's a mineral very similar to the pyromorphite, and hydroxyapatite would be expected to form. But this is a thermodynamic program, it's equilibrium. It would be expected to form, but we don't know about its kinetics. So an SI of 5.13 is quite low, so hydroxyapatite might form, but on the other hand, if there's some kinetic barriers, it needs to overcome activation barrier to form, then maybe hydroxyapatite wouldn't form. But certainly it's supersaturated with regard to that. It wants to form if it can. And in fact, if I look down that list, that's the only thing there. You'll notice that there's no lead there, but then there's no lead minerals, because if you look at our input data, I didn't put any lead, so there's not going to be any lead minerals there. So a couple of things to look at here is just I wanted to explain just a bit further is the value for alkalinity is given as 4.65 times 10 to the minus 4. And I inputted that at the top here. So let's check, what does alkalinity mean? Well, alkalinity means it's regarded as the acid neutralizing capacity of a water. So in experimental terms, what it means is that if you take a water such as this one, 7.35 pH, if you lower the pH to 4.3, then the amount of hydrogen ions you've used to lower the pH down to 4.3 will be equal to the alkalinity. What's happening is that as you lower the pH to 4.3, what's happening is certain species are being protonated. So, and the main species in the water that are being protonated in this particular water are the carbonates, and you've got phosphate being protonated too. So carbonates and the phosphates will be protonated. You've got sulfate in the water as well, but actually sulfate exists as in solutions at 4.3 as SO4 2 minus predominantly. So if you've got any HSO4, any species of, I'm going to get this wrong, but sulfate will, if you've got any HSO4 minus, then it will want to, it won't, oh, I'm not going to talk about sulfate. It's sulfate with carbonates. As you add acid, then it will mop up the hydrogen ions. But in the case of sulfate, sulfate can't mop up any more hydrogen ions, because in that, when you go down to pH 4.3, you've still only got SO4 2 minus present. You have to go much further down in pH, much lower than 4.3, before you start making any HSO4 minus species. So sulfate and phosphate and carbonate behave a little bit differently. It might be better actually to show you in a picture what I mean by the alkalinity. So I'll take up a Word document here. Get rid of this screen, remove that. So what I mean by alkalinity is, I had some data here. I'll stop this for a moment. So this is the equation. I've just written this equation out for alkalinity. So alkalinity equals concentration of HCl3 minus plus twice the concentration of CO3 2 minus plus OH plus 2 times the phosphate concentration plus the concentration of HPO4 2 minus, and then subtracting the hydrogen ion concentration and subtracting HSO4 minus concentration. So why the number 2 here and the number 2 there? The reason is that what we're trying to do with alkalinities is to know what species will absorb the hydrogen ions as you go down to pH 4.3. At pH 4.3, in terms of carbonate phosphate, you've got these two species here. So H2CO3 and H2PO4 minus. So in order for, at pH 4.3, going to pH 4.3, this species, the HCO3 minus species, will accept 1 proton. So therefore it's given a value of 1 proton. This one here, you multiply it by 2, because in actual fact 2 protons are needed in order to get down to H2CO3. Likewise over here, the species present at pH 4.3 is H2PO4 minus. So it only takes 1 proton to take HPO4 2 minus. Sorry, it only takes 1 proton to take HPO4 2 minus down to H2PO4 minus, but it takes 2 protons to take the PO4 3 minus down to H2PO4 minus. So this is the total alkalinity equation, and quite often with Phreeqc it's usually worth checking that things are working, because actually Phreeqc does work really well, but you need to be confident about what it's doing. So in actual fact, Phreeqc has told us what all these concentrations are. So if we added all of those up together, then we should get the alkalinity that Phreeqc has. So let's have a look at Phreeqc. So if we go into Phreeqc, let's look at the hydrogen carbonate concentration first. So what you can do is block this, like so forth, and do you can't do you'll have to do Control C to copy. The mouse, you can't right click to copy, so it's Control C to copy. Go into an Excel program. I'll open a new sheet and do Control V. So that's hydrogen carbonate concentration, and then go back into Phreeqc, and the next one was this one here. No, it wasn't. It was this one, sorry. And Control C and go back, Control V into Excel and import the values. And so you should end up with a list. Now one of the things it is at the moment is when Phreeqc's imported them, Okay, it's done them on separate columns. So there's all the data. This is one here is the one I made earlier. So there's my list. And what I did down here, this concentration value, is where I needed to. I multiplied by 2. So this value is the same as that one, but this one is because carbonates multiplied by 2. And like with the phosphate, PO4, 3 minus is multiplied by 2. And my total is 4.57 times 10 to the minus 4. So this is the alkalinity is adding all of these up, and this is my number, 4.57. If we go back to Phreeqc, the alkalinity isn't quite 4.57, it says 4.65. The difference is there is some alkalinity, contribution to alkalinity from these other little ion pairs. They contribute also. So Phreeqc is calculating those. But because we've got an alkalinity that's similar to the Phreeqc value, we kind of know that it's working. So one of the important things about Phreeqc is always check it is working, it does work, but by you checking it's working, you get more familiar with how it works. And actually that's a skill in using Phreeqc. So I'm going to stop there for the moment on this little example, and then I'll give another example later on.